This is an introduction to inferential statistics and correlation. Just as a reminder, descriptive statistics help us organize and describe a set of data. Inferential statistics allow us to make inferences or predictions from a smaller group to a larger group, from a sample to a population. Generally, inferential statistics are used after descriptive statistics, not instead of descriptive statistics. So you almost always are going to be using descriptive statistics. In evaluation, we may occasionally add inferential statistics as well. And inferential statistics are only appropriate if you have a representative sample of a population, or in the case of our evaluations, if you have 100% of your population. We have everybody that was in our class. So we're going to be talking about correlation. That's the one inferential statistic we're going to be working with. Correlation identifies if there's a relationship between two variables. Most of the time, two questions. Is there a relationship between the data in two of the questions that we asked in our level 1 or level 2 or level 3 or level 4 evaluation? It identifies if there's a relationship, and it describes the nature of that relationship. Now, correlation is not causation. I want you to say that out loud right now with me. Correlation is not causation. This is the biggest mistake that I see people make with correlation. Just because there's a relationship, we don't know if one of the things causes the other things. So for example, we know that there's a correlation between income and education. The higher people income, the more likely they are to go to school. The less income people have, the less likely they are to go to school. That's a correlation. What we don't know is which of those causes the other. Is it because people have more money that they go to school, or is it because people go to school that they have more money? We don't know the answer to that with correlation. All correlation tells us is that there is a relationship, and then it describes the nature of that relationship. And again, I'm saying it over and over and over and putting it in red because some of you, I guarantee, will, as you write up your assignment, try to tell me that something causes something, and that's not true. You don't know if it's true because correlation doesn't tell us that. Then finally, the last thing I want to mention is that correlation can only be used with interval variables. So remember, interval variables are the variables that are actually numbers. Correlation cannot be used with categorical variables. So all those Likert scales, you cannot use correlation with those. There's other ways to compare categorical and nominal. You can't use nominal variables either. There's other ways statistically to compare and create predictions from categorical and nominal variables, but we are not covering them in this class. All we're talking about is correlation, and all correlation works with are interval variables. So as I said on the last slide, correlation identifies if there's a relationship between variables, and it describes the nature of that relationship. Now, the way that it describes that is both in the direction of the relationship and the strength of the relationship. So in terms of direction, there's a positive relationship, and if two variables have a positive relationship, it means that they move in the same direction. So as one variable goes up, the other variable goes up. As one variable goes down, the other variable goes down. So positive doesn't mean they go up. It means they move in the same direction. Of course, the other direction is negative, and with a negative direction, the variables move in opposite, or as I usually refer to it, inverse directions. So as one variable goes up, the other variable goes down. As one variable goes down, the other variable goes up. So one thing that we're going to find out through correlation is the direction of the relationship, whether it's a positive or a negative direction. And then the other thing that we're going to find is the strength of the relationship. When we get our correlation number back is going to be a decimal point, and this chart shows the generally agreed on conventions as to how you can describe the strength. So you see from 0 to 0.2 is a weak relationship, or essentially no relationship. from point 2 to point 4 is a weak relationship, point 4 to point 6 is a moderate relationship, point 6 to point 8 is a strong relationship, and point 8 to 1.0 is referred to as a very strong relationship. Now, I referred a minute ago to the correlation number. Actually, what it's referred to is the correlation coefficient. So when we do our correlation in Excel, the computer's going to come up with a number for you, and that number is the correlation coefficient. That number is represented by the letter R. So let's do some examples. Let's say that we had a correlation coefficient of 0.7. What does that tell us about the relationship between these two sets of variables? Well, because it's a positive number, we know that there's a positive relationship, which means as one of the variables goes up, the other variable will also go up, or as one of the variables goes down, the other variable will also go down. And it's 0.7, which we look up on our little chart, and we see that that's a strong relationship. So we can describe this relationship as a positive, strong relationship, that there exists a strong positive relationship between these two variables. Let's do another example, point 4. So again, first thing we look at is the direction. Again, it's a positive number, so we see that it's a positive relationship. As one variable goes up, the other one goes up. As one goes down, the other one goes down. The number is 0.4. We look that up on our chart and we see it's a weak relationship. So what we can say about the correlation between these two variables is that there is a weak positive relationship between these two variables. All right, let's do another one. Minus 0.8. So first thing we look at is the direction. We see that it's a negative number, which means that as one variable moves up, the other variable moves down, and vice versa. 0.8, we look it up on our chart, and we see it's a very strong relationship. So what we can say about this is that these two variables have a very strong inverse relationship. And again, I tend to use the word inverse because it's easier for people to understand than the word negative. Another example, an R of 0.1, a correlation coefficient of 0.1. So first thing we look at is the direction. We see it's positive, so that the variables will move in the same direction, whether that direction is up or that direction is down. And we see our strength is weak, in fact, very weak. The way that I would describe this is I would say there is essentially no relationship between these two variables. And I wouldn't even talk about if it's positive or negative, because who cares what the direction is if there's no relationship? In fact, the next example I have is an R of minus 0.1. And again, we know now that that's a negative relationship, an inverse relationship. As one goes up, the other moves in the opposite direction. But because it's 0.1, because it's essentially no relationship, I don't even talk about the fact that it's an inverse relationship. I just say there's essentially no relationship between these two variables. So that's one thing that we can find using correlation. But we can do even a little more work with correlation. There's another thing with correlation referred to as the coefficient of determination, which is just a fancy way of saying variance, and that's expressed as R squared. And when we use Excel, we're going to be able to get our R, but we're not going to be able to get our R squared. But of course, the way you square a number is you just multiply it times itself, right? If I want to square the number 7, I just go 7 times 7 is 49. That's the square of 7. And that's how we're going to figure out the coefficient of determination. Now, what the coefficient of determination does is it lets you know how much variance in the relationship can be explained by the relationship. So let's do some examples. All right, our R is 0.7. So because of that, we know that it's a strong positive relationship. We multiply 7 times 7 and we get 0.49. And what 0.49 tells us is that 49% of the variation in one variable can be explained by the other variable. So if, for example, we were measuring education and income, what this would tell us is that 49% of education can be explained by income. That's pretty cool that statistics can figure that out for us. All right, let's do another one. So R is 0.4. Our correlation coefficient is 0.4. Because of that, we know that there's a weak positive relationship between the two variables. We square that by taking 4 times 4, and we get 0.6. And what that tells us is 16% of the variation in one variable can be explained by the other variable. So if one variable is students, the amount of time they spent studying for a test, and the other variable is their happiness with the course, only 16% of the variation in how they did on the test can be explained by their happiness with the class. So again, we don't know which one causes the other one because correlation is not causation, but we can get a lot of description about the relationship and the variance and what's predictive of the variance. All right, let's do a couple more. R equals minus 0.8. What this tells us is that there's a very strong inverse relationship, right? Very strong because it's 0.8, inverse because it's a negative number. And when we square that, 8 times 8 is 64, we see that 64% of the variation in one variable can be explained by the other variable. In our next example, R equals 0.1, and as I said before, 0.1 is essentially no relationship. So we say there's essentially no relationship. And if there's no relationship, there's kind of no point in going forward with the R squared, because in fact when we do that, what it tells us is 10% of the variation is predicted, by the two things. So it's just useless to talk about because there's no variation. So, so that's correlation. Now I want you to do one yourself. So here's a set of data, test scores, and hours of TV watching that the student does per week. The R, the correlation coefficient, is 0.6. So what I want you to do is to figure out the R squared and then to figure out what you can say about test scores and TV hours per week. And when you think you've figured it out, when you think you have your own answer, go ahead on to the next slide. Here is the answer. So the R we already knew was minus 0.6. You calculated the R squared, or the coefficient of determination, by multiplying 6 times 6, which is 36. With these two numbers, we can say, because of the minus 0.6, that there's a moderate inverse relationship between hours of TV watched per week and test scores. And because of the 0.36, we can say approximately 36% of the variation in test scores can be explained by the hours spent watching TV. Now you'll notice that I said approximately 36%. The reason I said approximately is because when you get your R, when Excel gives you your correlation coefficient, it won't be minus 0.6. It'll be like 6 or 7 or 8 decimal places long, and most of us just chop that off to 1 or 2 decimal places. Because of that, you lose some of the precision of the information, and that's why I like to say approximately 36% of the variation, just to cover my bases a little bit. So that's correlation. Correlation lets you identify if there's a relationship between two variables. It describes the relationship in terms of the direction and the strength. And by using the R squared, the coefficient of determination, you can also identify the amount of variance that's explained between the two variables.